This is a presentation on secure track verification, which is used for ADSB position verification. I'm the presenter, Bill Wiley. The date's 10/15/2020 for my course CS 6263. This paper was presented at the 2015 IEEE Symposium on Security and Privacy. The authors are Schaefer, Linders, and Smith. Premise: the position, which is broadcast from an aircraft, can be verified by ground-based stations along the route of flight. To verify that the ADSB information displayed on the air traffic controller's screen actually originates from the actual aircraft. Overview: today I'm going to give a brief summary of how the ATC system works, how traffic is deconflicted today, what TCAS is, the Traffic Collision Avoidance System, what ADSB is, the Automatic Dependent Surveillance Broadcast, which is a system where the aircraft broadcasts its position, some vulnerabilities and possible security mitigations that are being discussed. This is a highly researched area at the time. There are many, many papers out on it. How does the air traffic control system work? Well, the primary way things are deconflicted or separated today is with SSR, the Secondary Surveillance Radar. As a backup, aircraft, all passenger carrying aircraft have TCAS on board, which is Traffic Collision Avoidance System. And ADSB is being implemented into the system that's making big footholds, and it's got a lot of promise. Automatic Dependent Surveillance Broadcast. Secondary Surveillance Radar. It's termed secondary because the transmission information actually comes from a transponder on board the aircraft. SSR transmits on 1090 megahertz and receives on 1030 megahertz. And a primary surveillance radar would be a skin paint where the actual reflection from the middle of the aircraft comes back to the controller. SSR radar has a rotation rate of about 5 to 12 RPM, has a beam width of 2.5 degrees, transmits on 1090 and receives on 1030. And when interrogated, the aircraft transponder transmits the barometric altitude and the call sign, known as a squawk. The controller can get a rough heading and airspeed from algorithms from successive radar returns or blips. And it will show if the aircraft, and the controller screen will show if the aircraft is climbing or descending. So here's a brief depiction of what the aircraft controller sees. This particular display right here is BAW, which is British Airways Flight 9030, and the C after it indicates that it's an altitude encoding transponder giving the altitude. And you're going to find that almost all transponders within busy airspace are altitude encoding. In addition to ground radar, there's TCAS, Traffic Collision Avoidance System. This is an independent system that every aircraft, every passenger carrying aircraft has on board today. And what happens is when there's a conflict with two aircraft, usually co-altitude, one pilot is commanded to climb, the other pilot is commanded to descend, thus giving separation between the two aircraft. Its range is about 20 nautical miles. And it uses the same frequency, interrogates on 1090 and responds on 1030 megahertz. And here's an example of the display that the pilot will see. Now, this icon here is an advisory icon. It shows that the aircraft is 1,000 feet above and in a climb. And here is another icon, a white icon, 1,100 feet below and in a climb. Now, this is an advisory over here, the amber, showing 1,000 feet above and in a descent. And this is an alert where both pilots would get commands. You can see that there's only 100 feet of separation. with the target actually climbing. And that brings us to ADS-B, Automatic Dependent Surveillance Broadcast. So rather than being illuminated by ground radar, the aircraft internal GPS transmits position, call sign, altitude, heading, and airspeed. So the controller will have a very accurate position and altitude, heading, and airspeed information. It's dependent because the data is dependent only, say, from the aircraft data. It's received by ATC, and it can also be received by other aircraft having ADS-B receivers. This is a vast improvement for the FAA over secondary surveillance radar. The accuracy is much greater, and the update rate is also much greater. Updates about once every half a second. Accuracy being down to 10 meters. Here's an example of the ADS-B message format. There's no timestamp on the message, and the messages are transmitted about every half a second. See, it's 112 bits, the ADS-B message being 56 bits. Now, this message can potentially be modified by an attacker, or actually even originated by an attacker, to give any position, airspeed, and altitude. So a ghost target can be presented to the controllers and other aircraft in the area. Well, here's the FAA slide depicting how ADS-B works. The aircraft receives its information from GPS, and it can also transmit to GPS, which can transmit to other aircraft. It can transmit aircraft to aircraft, and of course from aircraft to a ground station, to the air traffic control. ADS-B has a lot of benefits. Self-separation without ATC, so aircraft can be aware of each other and separate without the need of a radio call from air traffic control. The pilot can determine final approach and runway occupancy many miles out. Visual flight rule like separation in all weather conditions. So when weather goes into IFR conditions, you can't see aircraft to aircraft, and spacing has to be increased between aircraft, slowing things down. ADS-B would make possible air traffic control in non-radar airspace over the oceans. You could possibly have self-determination of spacing behind other aircraft, and possible self-determination of traffic patterns. So pilots could line themselves up behind the preceding aircraft for final approach. ADS-B signals are not encrypted. They can be spoofed, and they do not depend on the actual transmitter location. The transmitter can be at any location. And of course, this can cause confusion to the air traffic controller and other pilots in the area. Several potential attackers can be an inside attacker, malicious airport aircraft passengers could actually have an ADS-B transmitter on board the aircraft. Remote attackers, ground station attacks, or air attacks. So you can have a sophisticated attacker like a nation state, has knowledge of the ADS-B format, has knowledge of the national airspace and ATC procedures, and has resources. And then we have an unsophisticated attacker, which would have none of those. Possible attacks, eavesdropping. Well, eavesdropping really is done today. FlightAware, the service, uses ADS-B to determine the actual real-time position of aircraft. And of course, eavesdropping can make a physical attack using real-time data much easier. Jamming, well, the ground station can have a flood denial. The transmitter has to be near the ground station. Or an aircraft flood denial, where transmitter needs a high power jamming signal, or it could be on board the aircraft. Message injection, that's more difficult and can cause fake targets to appear, would only be done by a sophisticated attacker. Again, message deletion by a sophisticated attacker, message modification by a sophisticated attacker, and denial of service requires resources and multiple transmitters. So my paper is on secure track verification and verification that the transmitter is the aircraft. The authors use the term poser, which is the same as aircraft or a mobile node, and verifier, which are ground-based receiving stations that verify that the position and track is accurate. A lot of good attributes of secure track verification. It's passive. It does not require any time synchronization among verifiers. It does not need to keep the location of the verified secret and does not need specialized hardware. So the authors would use at least 3 ground stations as verifiers. The time of arrival of successive transmissions at 3 ground stations, X, Y, and Z, are recorded. The time difference from the source to travel from point I to point J, so the aircraft would be traveling from point I to point J, is determined delta IJ. And then the propagation time to each ground station is determined by the distance as calculated from the ground station to the reported position of the aircraft. That distance is divided by the speed of light to give the time of propagation. And using this information, equations can be formed. The time and position of the target, as claimed in the paper, I and J are denoted by claimed C sub I and C sub J. At verifier X is denoted by V sub X. The time span between 2 transmissions of 2 locations, CI and CJ, is denoted by delta IJ, and that's just the time difference, the time of arrival of the 2 signals. And the time of arrival is noted by Tx sub I. So here are the conventions of time span. Delta IJ is equal to the time of arrival of J minus the time of arrival at X of I. And the propagation delay is delta Xi, and that's equal to Tx sub I minus, or Tx sub J minus Tx sub I. Values are derived by local timestamps or overlines, so there would be an overline above the deltas and t's to denote that the timestamps are local, honest. And here's how the mathematics is done. Each pair of the ground stations, so here we have ground station X and ground station Z. The possibilities given those times of arrivals form a hyperbola. Here it is for X and Y, that forms that hyperbola. And here it is for Y and Z, that forms that one. At the intersection is where the origin of the transmission occurs, which is denoted as P sub 1 here. So our ground stations would be at position PX, there's PY, and there's PZ. So the only valid location of the transmission would be here, where the intersection of those 3 hyperbolas occur. Okay, the drawbacks to this system. It can't be utilized by airborne aircraft. This will require network between the 3 ground stations and synchronization to see that that point is a valid point. And there will be problems with a denial of service attack where the images are flooded by many ADS-B transmitters. So there's other valid ways to secure and verify that a signal is valid with ADS-B. One proposal is to use public key infrastructure with a public and private key issued to all of the aircraft. Aircraft Address Missions Authorization Code, AA-MAC, where each aircraft is issued an address, kind of like a MAC address. Kalman filtering, which is a way of predicting a present position given previous positions. Multilateration, where 3 or more stations receive the signal at once and can triangulate the position of the transmission. Use historic traffic patterns, where air traffic control would know historically where the aircraft travels and can verify their position in that. And then something that it's not really addressed too much is the use of TCAS to verify the position of an aircraft. So public key infrastructure is much like the internet, where secure communications are done over in secure channels. Disadvantages, there's no compact encryption structure. This would mean for decreased inefficiencies in ADS-B and increased message length. And for every receiver, unique encrypted ADS-B messages are required, which would require a separate public-private key pair. Here's a diagram of multilateration with 4 different stations, a little bit like GPS, where that radius to the target would all appear at in a location where the circles intersect. Position can be verified in that fashion. Aircraft Address Message Authentication Code. We would assign a unique identifier to each aircraft, like a MAC address, and this is compatible with existing protocols and would have a relatively low cost for other security proposals. Kalman filtering is a mathematical way of predicting a position given the previous positions of velocities. It's already used by air traffic control in the SSRs, ground radars. And vulnerability is vulnerable to a fake location data injected with a slow rate. It requires more processing time and higher computational complexity. And it's vulnerable to a denial of service attack. However, it can be used on board the aircraft to verify ADS positions of other aircraft. Fusion, and that's the integration of different data sources to get a more accurate position. It's already proposed by the FAA that would use the primary radar skin paint to verify that the ADS-B return comes from the same aircraft. Advantages: no modification of ADS-B messages required. Radar is already in place. Data is not synchronized by time or position. Traffic modeling. Well, that's used the historic traffic control data to verify position. Use of received signal strength and possible use of angle of signal arrival. Another idea is to use TCAS. Just keep that same TCAS transmitter receiver on board the aircraft that's already installed. And TCAS gives altitude, bearing, and range information, uses the same frequencies, 1090 and 1030. And its major drawback is it has low signal strength, and it would only be applicable to about 20 miles for verification. There are many other studies I've drawn analysis of vulnerabilities by Manish and Kabosh, exploring potential AWS vulnerabilities by Macaulay, Prabha Pradesh, authentication using retroactive key publication, safety assessments of ADSB and ASA by Andrew Zetlin, and TCAS ADSB by Zhu. So today, briefly in summary, I covered the ATC system, TCAS, ADSB, the vulnerabilities, how the secure track verification would work, and some other possible security mitigations. Please email me if you have any questions on this. I'll be happy to answer. I've had a considerable experience with TCAS, ADSB, and the air traffic control system.